me introduce our first speaker is David Terman from The Ohio State University, where I was fortunate enough to spend a few years. I learned a lot about giving talks from Dave and always enjoy his presentations. And now we'll hear the latest work he's doing on the dependence of neuronal firing on cerebral capillary blood flow. So Dave, the show is yours. Now, please just type questions in the chat. And
let me know if there's anything in the chat, because often I miss those. But
clarification, I'll save it for the end.
Okay. Well, thanks, John, for inviting me. It's really a pleasure to do this. This is joint work with a surgeon on campus, Yosef Hassani, who works on issues related to stroke and small vessel disease, and an undergraduate, Liam Chen. And I'm going to talk about, in this short talk, I'm going to try to combine three models, actually. One for blood flow, one for the electrical activity of neurons, and one for ATP production by the mitochondria. So the idea is that, blood releases oxygen into the tissue, and the oxygen is used by the mitochondria to produce ATP. So that's the energy. The energy ATP is used to maintain the pumps, sodium, potassium pump. And of course, the pump is needed to maintain the ion gradients, and the ion gradients are needed to maintain spiking. So if you have impaired blood flow, the oxygen levels will go down, the ATP levels will go down, the pump strengths will go down, and then potassium will accumulate in the extracellular space, because every time the neuron fires, it releases potassium into the extracellular space. And if the extracellular potassium gets too high, that leads to bad things. Depolarization block, spreading depression, spreading depolarization, stroke, and things like that. So here is just some numerics. If the ATP level is high enough, then, sorry, I'm not very good at this. The cell can maintain spiking at some rate, and the potassium, let's see if I can do this. I think I had too much coffee today. Oh, well. The potassium levels off at some normal level, but if the ATP level is low, then as the cell spikes, the potassium builds up, and if it gets above some critical value, then the cell will go into depolarization block, and that could initiate spreading depression or depolarization. So here's some questions we were interested in. Is one, very basic: how do changes in blood flow impact a neuron's ability to maintain firing at a given frequency? So presumably, the faster it fires, the more potassium builds up. So if it fires too fast, it might not be able to maintain that firing. So we asked, what's the maximum frequency a cell can fire given conditions for the blood flow, how much oxygen and ATP there is? And actually the question that initiated this project, this surgeon asked me was, do heterogeneous capillary flow patterns result in lower brain tissue partial oxygen pressures? By the way, I use the phrase partial oxygen pressure throughout the talk. Partial pressure, that's just very closely related to the oxygen concentration. So if I say partial pressure, it just means really the concentration of oxygen. So there's a number of studies lately that have indicated that as we get older, perhaps, our properties of blood flow, like diameters or response to signals or whatever, becomes more heterogeneous. And these heterogeneities can result in lower oxygen levels, and that could lead to various diseases. So an outline of my talk is I'm going to consider the three components separately models. And so I'm going to throw a lot of equations at you, but I'll just try to highlight what's important for this talk. So I'll talk about each component separately, and then I'll try to couple them all together. So I think here's the neuron. So here's a lot of equations. This, I think you're the most familiar with you have the usual membrane equation. Of course, what's different between this and the Hodgkin-Huxley is that the Nernst potentials are not constant. They depend on concentrations of sodium and potassium. So we need equations for sodium and potassium inside and outside the cell. You think I can do this here? Yeah, that term there corresponds to the uptake of potassium by astrocytes. So, you know, astrocytes is one of the main things that buffers extracellular potassium. So in that equation, the astrocyte membrane potential VA is just assumed to be constant. And there's an equation for the pump. Let's see if I can do that. Where is the, there it is, the pump. The pump depends on, I threw in a term that you usually don't see related to ATP there. So for now, I'm going to assume that ATP is constant. And then when I talk about the mitochondria model, then ATP will, you know, change. But for now, let's assume it's constant. And I'm going to have an excitatory periodic input to the cell at different frequencies. I'm going to ask, what is the largest frequency that the cell can maintain firing? So here, I just, like, for example, in this panel, the ATP level is at some level, I lost this thing, whoops. And the frequency, well, 4 hertz, and GKA is 0. That means there's no astrocyte. And the cell has no problem maintaining firing at that frequency. If you go to the middle panel, I lower the ATP levels from 1 to 0.1. And the cell goes into depolarization block. There it's still at 4 hertz. In the right panel, it's at 10 hertz. But I added the astrocyte, and it has no problem maintaining the firing at 10 hertz. Okay, so that's the neuron model. Now for the mitochondria. This is the based on the Magnus-Kaiser model for ATP production. And again, there's lots of equations and stuff. The important thing to know is that it depends on oxygen, and it produces ATP, okay? And so now, PA, in that red box there, that's PAVJO, that's the, PAV is the average oxygen partial pressure in the surrounding tissue. So some tissue surrounding the neuron, that's the average amount of oxygen. And I'm assuming that's constant now, okay? That has to change when I introduce the blood flow model, but for now it's constant. Now for us, something that's going to be very important is the oxygen consumption rate. At what rate is oxygen being consumed? And that's the term gamma PAV JO. JO is basically the consumption rate. But if the tissue level is too low, then that goes down. So you multiply it by that's gamma PAV. So that's the, so we'll need the oxygen consumption rate later in the talk. And notice that this depends on calcium. There's an equation for calcium in there. And you would think that there's some way for the neuron to tell the mitochondria what its energy needs are. So if it's firing faster, maybe it should produce more ATP. So the way I put that in the model is I assume that kind of the intracellular cytosolic calcium goes up if it fires more. So what I do is I add the so-called Lee-Rinzel model for cytosolic calcium. And in that model, there's one of the variables is IP3. So in my model, IP3 is a parameter. And if you increase IP3, that will increase the amount of calcium coming out of the endoplasmic reticulum. And that'll increase the ATP production. So the way the neuron communicates its energy needs to the mitochondria is through this parameter IP3, but I do not explicitly model how that's done. I just assume it's a parameter. Okay, and so, I use XPP to solve these equations. On the left there, you see the response to different levels of IP3. If IP3 is high enough, 0.2, then you get these nice calcium oscillations. And if IP3 is low, then calcium stays low. And you can also plot the consumption rates. Like I say, the consumption rate is going to be very important. And you can see how the consumption rate and ATP production depends on, for PAV, which is the average tissue oxygen levels, or IP3. So if the tissue levels are low or IP3 is low, then the consumption rate is low. And if they're high enough, then the consumption rate goes to some elevated level. All right, so now I want to start combining the model. So how do we combine the neuron and the more Magnus-Kaiser model? Well, they're coupled through the cytosolic ATP levels. So in the previous slide, I didn't have anything related to the neuron, but so what we do is we add a term corresponding to the pump. So the pump is going to consume ATP. So the equation for ATPI depends on the mitochondrial production, which is this term in here, and the consumption by the pump. And one can actually analyze that mathematically using fast, slow analysis. So I'll just flash a few slides here of panels. The slow variables are the extracellular potassium and the cytosolic ATP levels. So if you fix ATP and you draw the bifurcation diagram, you think of Ke as a slow variable. So if it's constant, then you get a nice bifurcation diagram like that with a homoclinic orbit and things like that. And down here, this curve is, so here at ATP, so for different values of ATPI, the homoclinic orbit changes. So this is the curve, if I can get it, of homoclinic orbits. And if you project the variables Ke and ATPI onto this thing, you see that you get depolarization block whenever you cross this homoclinic orbit. So using that, and well, it's a bit of a work. I construct a reduced model and et cetera, but one can compute how the maximum frequency that the neuron can respond depends on the average tissue oxygen level, PAV. So here I'm showing how the maximum frequency that the neuron can respond before it goes into depolarization block depends on either PAV, which was the tissue oxygen levels, or this parameter IP3. And I consider different cases with astrocytes or without astrocytes. With astrocytes, it can, this model can fire, like 50 hertz. And, but without astrocytes, it can't go really above like 20 hertz. Okay. So now the last piece of the puzzle is blood flow. So more equations. So there's a capillary and there's the tissue. So I use, omega B is the partial pressure in the capillary, and it satisfies some ordinary differential equation, because I think of the capillary as a one-dimensional cable. And in the tissue, this is steady state, okay? Steady state condition. You have a Laplacian of omega, so you have diffusion. And this is an important term. This is in here. This is the consumption of oxygen in the tissue. So if you increase the consumption in the tissue, you're going to have less oxygen. So the important parameters here are Q. That's the flow rate. That's how fast, how much oxygen is flowing through the capillary. So if Q goes up, you get more oxygen and presumably more ATP. MT is the consumption rate. Rate is the oxygen being consumed in the tissue. And then you need a boundary condition. So that's the boundary condition, okay? So in the remainder of the talk, I'm going to consider a simple capillary network. There's just 4 vessels. Blood is flowing to the right. And there's this nice software by Seacom that we use to solve the equations for blood flow. And what you can do is with this software is for different consumption rates, you can figure out what the tissue levels are. And what I do is I can consider the tissue levels averaged over where the blood is leaving this region. So each one of these curves tells me if you increase the consumption rate, then you're going to have less oxygen. So PAV goes down, and you can do that for different flow rates. So obviously, well, I don't know if it's obvious, but if you increase the flow rate, if more oxygen is entering the system network, then you're going to have more oxygen. So that's what that curve means. So now I want to combine the models. So how am I going to combine the models? Well, what I'm going to do is I'm going to assume that the rate at which oxygen is being consumed in the tissue is exactly the same as it's being consumed in the mitochondria. I mean, that's why oxygen is being consumed, because it's being used by the mitochondria to produce ATP. And I don't know if you remember what all these terms mean, but it means that these are the various consumption rates. But anyway, this gives rise to a map. The map says that if you tell me what the consumption rate is in the blood, from the previous slide, you can compute the average oxygen partial pressure. And from a few slides ago, I showed you that if you know what the average partial pressure is in the tissue, you can compute well, I have JO, but that's related to the consumption rate of the mitochondria. And so what we want to do is we want to find a fixed point of this map. So we just use MATLAB to do that. So this is kind of a busy picture, but what it shows is, see, if you tell me what PAV is, the actual average tissue oxygen, these various curves here are the consumption rate in the mitochondria. And there's different cases. There's with astrocytes are in black, without astrocytes are in red, and dashed is, and then I have different levels of IP3. On the other hand, if you tell me what the consumption rate in the blood is, in a previous slide, I said you can compute what the average tissue level is. So, and I do this for different flow rates. And the thing is, where these curves intersect is where the fixed points are. So what this says is if you tell me what the flow rate is, this is the combined model, I can tell you what the average tissue oxygen levels are, partial pressures are. This combines the consumption of oxygen both in the mitochondria and the tissue. And we have the different cases of with astrocytes and without astrocytes and different levels of IP3. So, and then a number of slides ago, I showed you that if you know what the value of PAV is, the tissue level, you can compute the maximum frequency. That's where I use that bifurcation diagram. So what I now have is if you tell me what the flow rate, that Q in the blood is, I can tell you the maximum frequency that the neuron can fire before it goes into depolarization block. And my last slide is the issue of homogeneous versus heterogeneous networks. So if let's assume that the total blood flow rate is Q for all 4 vessels. The homogeneous case is if all the flow rates of each of the vessels are the same, so Q over 4. On the other hand, the heterogeneous case is basically you choose random numbers, so the flow rates add up to Q. All right. So that, you know, heterogeneous flow rates. And what this curve shows is the dashed is heterogeneous, the solid is homogeneous. Sorry, I'm not doing too good. For different values of the flow rate. But anyway, this, you know, if you look at the black curves, the dashed is below the solid. So that means the heterogeneous case produces less oxygen for a given consumption rate than the homogeneous case. So it shows heterogeneities lower the average oxygen levels. And, oh no, this is my last slide. So then we ask the following question. For which values of Q, that's the blood flow rate, and IP3, that's ATP production, is the average oxygen level above some threshold? So the idea is that this threshold, you know, surgeons or doctors sometimes say that what is, you know, the pathological, when is the patient, you know, may have a stroke. And you say if the average level, oxygen levels get below some level, which I call P naught. So the question is how fast must the flow rate be? And IP3 is, you know, the ability of the neuron to communicate its energy needs to get above, so you guarantee that the oxygen levels are high enough. So using this analysis, we're able to draw a picture like this. So there's IP3 levels, there's the minimum flow rate, and there's different cases with astrocytes and without. So black is with astrocytes. And notice the dash curve, black curve, is above the solid black curve. So that means that if there's heterogeneity, you have to have a larger flow rate. You need more oxygen entering the system in order to keep the tissue oxygen levels above some threshold. And actually, that's my last slide. I didn't get around to doing a discussion. I guess as far as discussion, for me, it was just a question of, is one able to combine this model and compute how, the neurons firing depends on the flow rate and energy needs in a somewhat realistic model. I like to emphasize that even though I had zillions of equations and things, it looks complicated, that this is in some sense a minimal model. There's many, many, many things that are unknown and not included in the model. For example, how does the neuron communicate with the blood? Presumably as it needs more oxygen, that's going to communicate to the blood to dilate or increase the diameter or whatever. Those are really just parameters in our model, but they're very controversial how all that happens. So I did not explicitly model it. And I guess with that, I'll stop.
Thanks, Dave.
Should I stop the share?
No, hold on for a minute. So at the moment, the chat is empty, but so people could either type questions in the chat, or I'm trying to look over the participant list. So if you prefer, you can sort of raise your hand in the participant list if you have a question. And if you can't manage either of those and it happens to be quiet, then you could just unmute and jump in. So do we have questions? I can start with one. In reality, I guess there would be interaction of the blood flow with the astrocytes as well. Is that in the model at all, or is that something to think about?
I didn't really say that. There's a bunch of details I didn't say. In what I have, I just have that the consumption rate by the astrocytes is pretty much constant. It's that gamma function. But you're absolutely right there. The astrocytes consume energy, and that could depend on flow rate too, and things like that. So that maybe can be modeled in a similar way. But I just, in this simple model, I just have it basically be at a constant level.
So I guess with heterogeneity, with that additional detail in the astrocytes, it could get even worse. Like,
oh yeah.
Have even, yeah. You need even more flow. Okay.
There's, communication, of course, between the astrocytes and the blood, and
okay, so they can
that's where the communication probably takes place anyway. So.
Okay. Nice. All right. Are there any other questions? Okay. Yeah. Here we go. So, a question from Peter Thomas. When you were setting up the fast-slow analysis, how did you decide which variables are slow in this particular model?
It turns out that you don't really even need most of the mitochondrial model for it. So I think it's natural to have extracellular potassium. And then for the neuron, there's conservations of potassium and sodium. So, and if you use some electrode neutrality, you can basically get rid of the other ionic variables. So you're just really left with potassium, ATP, and then the memory potential and the recovery variable. So then it's kind of natural just to have those two variables, if that answers it. Okay, the first step is to reduce the model to a simpler one. And then it kind of pops out that those are the natural variables to choose.
Okay. And one final question before we go to the next speaker. This is from Mohammed Abdullah. Can these kinds of models account for delays between neurons, monitoring, signaling for, and satisfying their energy needs? And I guess more importantly, would this have significant impact on the network behavior? The delays.
I guess I wouldn't, explicitly throw delays in there, but I guess you can add processes that naturally, that have different time scales and take certain times to get above certain thresholds, and that would naturally introduce delays. And so that's, you know, or you get propagation along neurons or whatever. So that's how I would introduce delays, I suppose.
Okay. As far as the impact, if you want to follow up on that in the chat, feel free to type, but we should move on to the next talk. So thanks.